Lights cut through a mist of chilled air as the door to Dr. Michael E. Blackwell's quantum mechanics laboratory slides open. This is no ordinary research facility tucked behind a university crest or a government logo. It's a privately funded crucible of ideas, stitched together by corporate partnerships, government grants, and the founder's own ventures. The hum you hear is not just equipment. It's the sound of decades of accumulated ambition. For years, the common wisdom held interstellar travel as a problem of scale. Distances too vast, energy budgets too steep, human lifetimes too short. It was a problem solved in fiction, sketched on pages and screens. But inside these walls, those sketches are being made tangible. Dr. Blackwell is both scientist and entrepreneur, an inventor who learned to translate equations into hardware. His team is a mix of theoretical physicists, material scientists, systems engineers, and a few skeptics who stayed when the results began to arrive. They've rethought what a ship can be, from payload frames and life support to the heart of motion itself. The Quantum Genesis is their answer, a vessel that does not rely on pushing mass through empty space, but instead reimagines how space itself can be shaped and used. Funding here matters. Private ventures let experiments move faster than bureaucratic cycles, and corporate partners supply fabrication and integration expertise. Government grants bring oversight, measurement standards, and sometimes the skeptical rigor that keeps the extraordinary claims from floating unsupported. Together, those sources have allowed Dr. Blackwell to prototype at a scale usually reserved for decades-long national programs. That confluence of private ambition and public accountability is central to the story. The lab is an engine for innovation and a mirror for responsibility. This chapter of the story is about more than machinery. It's about a shift in perspective. Where others saw a distance to be overcome with brute force, Blackwell's team saw an opportunity. What if we stopped treating space like an obstacle and started learning to move within its rules? What if gravity, long a force to be resisted or adapted to, could be harnessed as the medium of travel itself? The answer, as their work suggests, lies in the Graviton drive, a concept that redefines propulsion by manipulating the carriers of gravity. In this lab, the improbable is given a timetable, rigorous tests, and a crew of people working the long nights to make the universe bend, not to their will, but to a new understanding of what is possible. This is not another rocket. The Quantum Genesis reads like a different category of artifact entirely, part spacecraft, part precision field generator, and part living experiment. At its core is a controlled infrastructure designed to create and manipulate concentrated fields of gravitons, hypothetical quanta associated with gravity. Whether gravitons are ever directly observed in our current instruments, the engineering approach here is pragmatic. Design systems that produce measurable, repeatable space-time effects and then refine them. Contrast this with traditional propulsion. Chemical rockets expel mass to produce thrust. Ion drives accelerate exhaust at high velocity for efficiency, but still depend on reaction mass. Solar sails ride photons, elegant but slow. Those systems all push against something external. The Quantum Genesis, by contrast, works with space-time itself. Think of conventional drives as rowers on a vast ocean. The Graviton drive is more like a boat that shortens the ocean in front of it while stretching it behind, letting the vessel coast without the same expenditure of propellant. Internally, the ship houses layered emitter arrays and control lattices, advanced materials and superconducting circuits that hold and channel energy in precisely timed pulses. Those pulses are tuned to generate focused disturbances in space-time, directional and controllable. The engineering challenge is immense. You need incredible precision in phase, amplitude, and geometry, so the fields add together in the right places and cancel elsewhere. Sensors map the local curvature in real time. Feedback loops adjust emission patterns to maintain stability. The result is a navigation system that doesn't fight gravity so much as sculpt it. Operationally, the Quantum Genesis is designed for long-duration missions. Without the need to carry astronomical quantities of propellant, payload fractions increase dramatically. Habitats, scientific instruments, and redundancy systems can be scaled up, making long-term human presence more feasible. The ship's design also anticipates layered safety, redundant control cores, passive failsafes that collapse field geometry gently if systems diverge, and evacuation modules that can detach and rely on traditional propulsion as a backup. It's a fusion of radical physics with practical engineering, a vessel designed to be audacious and survivable. This is what makes the Quantum Genesis different. It doesn't attempt to imitate known rockets. It reframes the problem. It turns the universe's baseline into a partner, not an opponent. That reframing makes interstellar distances less forbidding and opens a pathway to missions that would have been impossible under older paradigms. To understand the Graviton drive, imagine space-time as a taut sheet stretched across a frame. Most propulsion systems operate within that sheet. The Graviton drive reaches underneath the sheet and tugs gently at its fibers. Through precisely phased emissions, it generates localized regions where space-time is compacted ahead of the ship and stretched behind. The ship itself sits inside a bubble of engineered curvature. It doesn't experience the acceleration forces in the way passengers on a conventional rocket would. Instead, the bubble moves relative to surrounding space. Technically, this requires creating coherent directed fields, what the lab calls focused graviton waves. In practice, the team uses arrays of emitters that can be phased like an orchestra. Small shifts in timing and intensity change the shape and velocity of the bubble. Sophisticated control software translates mission goals, trajectory, destination, evasive maneuvers, into field configurations in milliseconds. There are profound engineering obstacles. Producing the necessary field strengths demands vast but transient concentrations of energy. The lab relies on superconducting storage rings, compact fusion injectors in early prototypes, and advanced capacitive networks to deliver pulses without damaging the ship. Material science plays a role too. Structural components must tolerate gradients in curvature and the subtle tidal effects that accompany space-time manipulation. That has driven novel alloys and metamaterials designed for stability under varying curvature regimes. Safety is addressed on multiple layers. Predictive models estimate local effects on nearby objects and on the ship's own systems. Real-time diagnostics watch for instabilities and deploy corrective pulses or, if required, a controlled collapse of the field that returns the vessel to conventional inertial motion. The mathematics behind it borrows from quantum field theory, general relativity, and numerical simulations of nonlinear systems. The team runs thousands of virtual trials before any real-world firing sequence. If the models are correct, the practical gains are extraordinary. Journeys that would once span human generations could be reduced to years or months. With carefully managed field dynamics, the drive can affect directional changes without the propellant demands of conventional maneuvers. That opens up mission architectures that include rapid exploration sorties, slow-burn scientific platforms, and even cargo shuttles that reposition habitats between systems. Beyond the immediate applications, the Graviton drive reframes research priorities. Navigation becomes a problem of field mapping and resonance matching. Interstellar medium interactions, dust, gas, micrometeoroids, are reconsidered through the lens of a moving curvature bubble. Communications must account for relativistic offsets in timing and signal paths. Each new challenge breeds innovation. Better sensors, improved error-correcting comms, and autonomous systems optimized for field-driven dynamics. Dr. Blackwell's lab is methodical. Early demonstration missions are unmanned probes that validate principles at small scales before committing a crew. Each success feeds back into design revisions, more efficient emitter geometries, refined control algorithms, and better energy recovery systems that recoup unused curvature work. The goal is not just to prove a concept, but to make it reliable, scalable, and crucially, safe for human explorers. The first demonstrations were modest, short hops in controlled test ranges where sensors could watch the slightest curvature change. The Quantum Genesis prototypes were unmanned at first, compact, instrument-laden hulls that performed programmed maneuvers while arrays of observatories recorded every variable. Those tests produced signature readings, shifts in local inertial frames, Doppler anomalies consistent with predicted space-time gradients, and visual distortion patterns that matched simulated ripples. Visualized, the effect is eerie and beautiful. Cameras show a warping halo, a faint, refractive shimmer surrounding the vessel as fields engage. Star fields appear to stretch and compress, and probe beacons launched ahead return data that indicate altered light paths consistent with the engineered curvature. In repeatable sequences, the craft slips forward in ways conventional thrust cannot produce. Distances between 2 points effectively shrink, while the interior remains calmly pressurized and unaccelerated. Scaling up, the lab moves from short hops to longer trajectories. Unmanned demonstrators traverse tens to hundreds of kilometers using field-driven translation, while telemetry confirms reduced energy costs compared to equivalent delta-V via conventional propulsion. Those results are presented not as speculation, but as reproducible experiments with measurements, error bars, and peer-reviewed modeling. Public demonstrations are cautious and deliberate. The team invites independent observers and collaborates with regulatory bodies to develop safe launch protocols and space traffic guidelines for curvature-driven craft. That transparency is intentional. The implications of bending space-time extend beyond a single vehicle. They affect orbital dynamics, satellite operations, and international norms about where and how such technology can be used. Demonstrations are therefore accompanied by detailed risk assessments, fail-safes, and commitments to open scientific verification. The emotional impact of seeing reality seem to bend is profound. For engineers, it's validation of months and years of work. For policymakers, it's a prompt to consider new frameworks for safety and access. For the public, it's an image that reframes humanity's place in the cosmos, a bridge between the earthbound present and a future where the distances between stars are questions of engineering and ethics, not impossibility. Dr. Blackwell's quantum mechanics laboratory didn't just produce hardware, it produced a new vocabulary for exploration. The quantum genesis is a symbol, an engineering prototype, and a cultural pivot. It asks society to decide how to steward a capability that changes what is logistically possible, how to allocate exploration priorities, how to ensure equitable access, and how to govern technology that literally reshapes the medium of travel. The practical benefits are immediate: larger payloads, shorter transit times, and mission flexibility that allows humanity to plan multi-system architectures rather than single-shot, one-way missions. The economic and scientific returns could be enormous. Faster transit translates to more frequent resupply, iterative science programs, and the spread of infrastructure to places that were previously unreachable. Yet alongside opportunity come responsibility and questions. Who controls access to such drives? How do international laws adapt to craft that can alter local gravitational environments? Dr. Blackwell and his collaborators emphasize transparency, data sharing, third-party verification, and regulatory engagement as part of their roadmap. They present the quantum genesis not as a proprietary gate to the stars, but as the start of a cooperative era in which private ingenuity and public oversight co-evolve. In the end, the story is human. It's about people who refuse to accept impossible as final. It's about careful experimentation, cross-disciplinary craftsmanship, and the steady conversation between bold vision and rigorous testing. As the quantum genesis prepares for its next phase of trials, the laboratory hums with the same mix of trepidation and exhilaration that accompanies every great leap. The Graviton drive is not an endpoint, it's the bridge. And in crossing it, we don't just travel farther, we learn to think differently about the space between us and the stars.
He's Dr. Michael E. Blackwell, scientist and engineer, and what you're about to see is the culmination of years chasing a simple idea. That idea is bold: turn gravity into a tool for transportation, for controlling energy, and for exploring the unknown. It began with childhood questions about falling apples and distant stars, grew through undergraduate MBA and PhD, and became a mission he couldn't ignore.
To pursue that mission, Blackwell assembled a multidisciplinary lab built to turn curiosity into hardware.
Physicists, engineers, and mathematicians, aligned on one goal and one standard. The data decides. They model fields, then we build them. Schematics to systems, equations to emitters. Every hypothesis faces a prototype, and every prototype earns its place through results.
Inside this facility, experiments move fast. Design, test, break, learn, and iterate. Data first, egos last.
High-risk, high-reward work, anchored by rigorous controls and safety protocols at every step. They push emitters, map distortions, and refine control until behavior and numbers match. No exceptions. The purpose is clear: transform gravity from a constant we endure into a system we command.
The culture bridges whiteboards and welders, simulations, soldering irons, and shared ownership of outcomes.
Daily questions drive us. Can fields steer ships, stabilize habitats, and harvest usable energy? Can we build propulsion that works with the universe instead of against it? This is the Quantum Genesis program, where that vision becomes real. Let's begin. In the beginning, he funded a small, exploratory program himself. Quiet benchwork aimed at one question: could we produce stable, controllable graviton field effects at laboratory scale? That independence let them prototype quickly, iterate daily, and follow the data, not a committee agenda. They built crude rigs, logged every pulse and oscillation, and mapped responses against our models. The goal was feasibility, not polish. Clear, repeatable signal over spectacle. The first milestone was a reproducible field signature, matching predicted behavior across multiple runs, with controlled inputs and blind analysis. Only then did they expand. Partnerships and grants followed after they opened the lab to external auditors and peer review of our methods and raw data. The validation wasn't a headline, it was a checklist: independent replication, documented uncertainties, and clear error bounds. That's what earned confidence.
Funding scaled infrastructure, clean rooms, magnetic shielding, precision fabrication, and safety interlocks, so experiments could move from fragile rigs to production-grade hardware.
They formalized test campaigns, calibration, stress, and failure mode analysis. Every subsystem was validated against performance specs before integration.
Collaboration expanded, industry partners for tolerances measured in microns, agencies for compliance, and a standing review board to verify results and safety.
Prototype to pilot line to flight-rated assemblies, the progression was deliberate, measurable, and documented end-to-end. That arc leads here. Quantum Genesis, the full-scale prototype, built specifically to test long baseline graviton field propulsion under operational conditions. Every major system reflects a single objective: sustained interstellar transit. This isn't a multi-role craft. It's a focused platform for deep space trials. She spans roughly 120 meters, supports a 12-person crew, and carries life support rated for multi-year missions, because real tests take time.
The living spaces are functional by design, but the critical infrastructure sits behind them: power conditioning, field containment, and continuous telemetry.
At the core is the Graviton drive, arrays of quantum field generators engineered for coherent, tunable emissions and tight containment. It's years of theory translated into hardware, with control software, diagnostics, and data pipelines built to catch what the eye can't. They've cleared internal readiness. Systems integrated, safety checks passed, oversight satisfied, and our independence in research direction preserved. Next comes the Interstellar trial, where the data will speak for itself. Let me start with why their approach diverges from conventional propulsion. Chemical and ion rockets rely on brute force, throwing mass one way to move the vehicle the other. That's powerful, but it scales poorly beyond nearby space. You expel reaction mass and ride Newton's third law. It works, but propellant dominates design, and the rocket equation punishes long missions. For interstellar goals, that inefficiency becomes the limiting factor. The required fuel grows to impractical levels, and performance gains taper. That's the wall we aim to bypass, without adding more propellant. The Graviton drive doesn't push on exhaust. It engineers the environment the ship moves through. Instead of fighting the universe, we work with it. They generate controllable graviton fields, tunable emissions, and use them to shape the local gravitational landscape around the vessel. By phasing, steering, and phase-locking these emissions, we sculpt field geometry. Stronger here, weaker there. So the surrounding space-time becomes our guidance medium. This is precision physics, not brute force. Understand the rules deeply, then configure them to do useful work with minimal waste. The result is a controllable, energy-efficient field architecture. They channel natural laws through coherent patterns rather than overpowering them. Quick primer. In quantum field theory, interactions are mediated by quanta, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak interaction.
Gravitons, while not directly observed, are the hypothesized quanta of the gravitational field. We model and target their coherent emission patterns to shape curvature consistently with established theory.
Engineering translation. Phased ring generators produce coherent graviton emissions. Feedback controllers lock phase and amplitude. Telemetry closes the loop, mapping emission quanta to measured field geometry in real time. Arrays operate in concert. Each generator contributes a beam with defined frequency, intensity, and phase. Together, they synthesize the target field configuration around the hull. These beams are coherent and directed, not diffuse. They tune them to induce specific gradients, translation, shaping, or stabilization, depending on the maneuver. Control software adjusts beam parameters continuously, correlating emission spectra with local curvature metrics. Small changes in phase yield precise changes in the surrounding gravitational field. Quantized emissions become an engineering tool. Billions of controlled pulses per second assemble a stable, low-entropy field shape we can command. Telemetry tracks emission counts, phase coherence, and topology error bars. When geometry drifts, feedback nudges the generators to keep the field locked on target. Now, the physics. Einstein showed that gravity emerges from space-time curvature due to mass energy. They exploit that framework, carefully and within its bounds. The drive creates controlled curvature without planetary scale masses by arranging fields that mimic the needed geometry locally around the craft. Practically, they configure curvature, so space is slightly compressed ahead and slightly expanded behind. The gradient is engineered, not guessed, derived from models and verified by instruments.
They call this a metric gradient, a designed slope in space-time geometry that guides motion, quantified by our curvature and topology measurements.
The ship isn't pushed in the classical sense. It slides along the curvature we've created, with inertial loads minimized by design. Contraction ahead brings distant coordinates closer. Expansion behind increases separation already covered. Navigation becomes the art of shaping that gradient on demand. The net effect is effective long-range transit without conventional acceleration profiles. Locally, we respect relativity. Globally, the engineered curvature changes path length through space-time. The mathematics are intricate, but the principle is elegant. Coherent, tunable emissions mapped by telemetry to stable geometry. Physics translated into a controllable medium for travel. One of the immediate human benefits is inertial comfort. During drive operation, the crew doesn't feel pushback or jolts, so work continues without strain. Fewer forces mean wider safety margins, calmer cabins, and continuous operations, even during long burns and course adjustments. With the Graviton drive, local spacetime does the moving, not your body. That gives us stable circadian rhythms, steady hand-eye tasks, and lower fatigue. Ergonomic stations stay aligned, and small details, like a steady coffee, translate into big gains in focus and crew health. Even at apparent high velocities, the cabin feels like free fall. Zero-spill protocols are easy, medical monitoring is calmer, and equipment remains within tolerances. That comfort compounds into safer shifts, longer watches, and fewer interruptions to mission timelines. Coffee doesn't slosh, racks don't sway, and the crew stays relaxed and alert. Human-centered design, backed by physics. It's more than comfort, it's safety. Smooth fields mean wider abort windows, benign emergency maneuvers, and predictable loads on every human and component aboard. Mission after mission.
Bottom line, human comfort drives uptime, and uptime drives mission success.
Now, applications. Focused graviton waves give us controllable metric gradients, letting us do work in space gently and precisely. That unlocks station keeping without thrusters, quiet rendezvous, and field shaping around sensitive payloads. They map distortions with precision instruments and tune them in real time. The result? Millimeter-level station keeping, soft dock approaches, and stable microgravity research platforms for long-duration biology, materials, and fundamental physics. For orbital logistics, engineered gradients let us hold mass without plume impingement, ideal for servicing telescopes, depots, and habitats. Heavy lift becomes cleaner and safer near assets that can't tolerate exhaust. Deep space probes benefit too. They can inject them on precise trajectories using gentle field ramps, preserving propellant for science, and increasing payload fractions to the outer planets and beyond. All of this stays grounded. Measured fields, repeatable settings, and clearly defined envelopes that operators can certify and auditors can verify.
Next demos, precision station keeping, heavy lift assists, and probe injection trials. Our roadmap, staged ground validations, incremental flight demonstrations, then full-up mission rehearsals. Every phase publishes open data sets and procedures so universities, agencies, and industry can reproduce and review the results.
Comparative timelines show why this matters. Missions that once took decades compressed to years, sometimes months, without sacrificing safety or science. Faster logistics cycles mean more frequent launches, more data returns, and a sustainable cadence for exploration and research. The door to interstellar work widens. Commercial services and public research both gain access to new destinations. Targets that were aspirational become practical. Nearby stars, deep Kuiper Belt science, and long-lived observatories in quiet orbits. The Quantum Genesis program proves these capabilities step by step, with independent oversight, documented tests, and community feedback loops. They invite partners to collaborate. Open protocols, transparent reviews, and shared tools that let anyone validate, challenge, and extend the work. This is the start of responsible expansion beyond our solar system, measured, testable, and inclusive. So that's the practical promise of the Graviton Drive. His vision is simple: responsible stewardship, full transparency, and milestones you can measure. Demonstrations, data releases, audits. So trust grows with every flight.
Upcoming, field mapping results, station keeping certification, probe injection trials, and logistics demos, each with peer-accessible datasets and clear pass-fail criteria.
He's excited to share every validation flight and open our portal so you can analyze the numbers alongside us. The universe just got more reachable, and we'll get there carefully, together. Thanks for watching. Join the community, review the data, and help refine the path forward. This is how we unlock the stars responsibly. Clear goals, transparent methods, and shared results, so the next generation starts from proven ground.